Okay. So hydrocarbons, it's an extension of organic chemistry. I mean, obviously, hydrocarbons are organic compounds. So we'll be coming back to a lot of the organic chemistry concepts that we've done. So what did we do? Nomenclature, like this time for every single different type of organic compound you study, starts off with nomenclature and structure and what type of isomerism and all of that. The second is your physical and chemical properties. Chemical properties is how they react. So we're going to get back to electrophiles, nucleophiles. Is there resonance? What sort of effects? Is it going to form a carbocation or carbanion? So we'll be touching on all of those concepts. So, keep coming back to it, keep revising it if you think you're not really confident, but it's not something that you're going to forget easily. So don't worry about that. This whole chapter, you can treat it as 4 smaller chapters because the whole thing is structured in such a way. Okay. So this chapter is hydrocarbons, right? What are hydrocarbons?
The carbons linked with the hydrogen atoms.
Compounds with hydrogen
and carbons.
Correct. So these are compounds containing only hydrogen and carbon, nothing else. No oxygen, no nitrogen. So we're not gonna look at any of those functional groups right now. So we're only looking at carbon, organic compounds containing carbon plus hydrogen only. So what are these compounds that you guys know of? What type of organic compound, like what all functional groups contain only carbon and hydrogen?
alkanes.
Alkanes, alkynes.
Correct, that's it. Alkanes, alkenes, alkynes. And there's a 4th type of compound containing only carbon and hydrogen, which is, these are all like proper straight chain ones, right? So we'll also be looking at the aromatic counterparts of this. So in this case, it is benzene and its derivatives like toluene and all of that stuff. When I say derivatives, I don't mean like phenol, aniline and all that. Basically, mainly toluene, benzene with a CH3 group or 2 CH3 groups, compounds like those. So you can treat this chapter as 4 different mini chapters. The structure is going to be the same. Structure in the sense what all you study about it. So first, there's going to be intro. Intro in the sense structure, name, isomerism, etc. Things like that. Special points about them. Then you have preparation. Where all will you get these compounds from? Then you have physical properties. This is like really tiny. It's mainly boiling point, melting point, density, smell, color, all of that. And chemical properties. So out of these, what you need to focus on mainly is preparation and chemical property. So these are like the main ones. And to some extent, like structure, nomenclature. Physical properties is like very easy. Don't skip it, but if there's any important parts, I will mention it, and that's the only thing you need to focus on. If there's like an anomaly, like you expect the boiling point to be low, but by chance if it's like really high, then the reason behind it and things like that. Only the anomalies. Focus mainly on preparation, chemical properties. These are like the more difficult parts of the chapter because they consist of like reactions, mechanisms, and all of that. And it's going to be the same thing. You're going to study all of this for alkanes, then for alkenes, then for alkynes, and for benzene. Okay, that's pretty standard. In fact, from now onwards, every organic chapter that you come across, 11th grade it's just the hydrocarbons, but in grade 12, you have each of the functional group. You have halides, you have alcohol, you have aldehyde. Every single chapter will have this particular order only. This is pretty standard. Okay. So I will treat it as such. We'll go through alkanes, then alkenes, then alkynes, then benzene. That's easier to like categorize and segregate. So we'll start off with alkanes.
For benzene, it'll be like benzene and toluene, right?
Yes.
No other derivatives, right?
No, I mean, if it's an alcohol derivative, you'll study it under alcohols. Now, since we are sticking only to hydrocarbons in this chapter, it's just going to be benzene and toluene. Okay. Start off with alkanes. So introduction, what are alkanes? Things you guys already know about it.
Single bond. Yes.
Single bond compound.
Yeah.
Do we say the formula also?
That's it. So they consist of only carbon, hydrogen with single bonds only. That's it. Other names to it. So they are also called paraffins. So word paraffin wax, like if you've heard of it, they call paraffin wax because they mainly contain alkanes. Okay. What else? What is the general formula?
CnH2n plus 2.
Correct. So all their formula take this form CnH2n plus 2. What is the hybridization of carbon in alkanes?
sp3.
sp3, because single bonds only, sp3. So that's why the geometry is going to be
Tetrahedral.
tetrahedral, correct. Okay. What else? IUPAC name. Do they have any special suffix? Like what is the format? N. They're literally alkanes. End with A. Okay. What else? Okay, good. What are the different types of isomerism you would find in these? Do you guys remember what all different types of isomerisms exist in organic compounds?
Structural isomerism and stereoisomerism.
Structural, yes. So within structural, you've got like position, chain, functional group, all of that stuff, right? So what all
Metamodism and total.
Yeah, so what all different types of isomerism would you find in alkanes?
Chain isomerism.
Positional isomerism.
Cool. Chain and position. Would you find any functional group isomerism?
There are
No.
two elements in it. So no.
Yeah, only two elements. Functional group. Metamerism, would you find it? You guys remember what is metamerism?
Resonating structures.
No. Isomerism, like this has nothing to do with resonance.
It's like esters and ethers and stuff. So
I
no.
effect and minus I effect thing.
What was that, Kaveri?
Plus R effect, minus R effect.
No, those are all electron displacement. I'm talking about metamerism.
It had something to do with esters and ethers. Yeah, like it's for like some specific kind of group.
Yeah, not for esters, but ethers, yes. This is a good hint.
It's the chain like around the oxygen, right? The length of the chains around it.
Correct.
On either side of it, sorry.
Yes.
Like alkene and alkoxy.
Yes. So same functional group, same number of carbon atoms and all that. But if the number of carbon atoms on this side and this side differ, like that's the only place where it's differing, then that is called metamerism. Yeah. Like for example, you have one carbon atom and 3 carbon atoms here. And you have 2 plus 2. This group of compounds, chain length, well, like ether hai, 2 sides of it, like overall 4 carbon atoms only. Position, functional, same functional group, but the number of carbon atoms is differing in both these cases. So these two are called metamers. So this type of isomerism is metamorism. Yeah. So now, do you find that in alkanes?
No.
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 So that's all the structural isomerism. You find only chain and positional isomerism. Now coming to geometrical isomerism, do you think there is a possibility of stereoisomerism?
Ma'am,
Hmm?
I didn't understand why metamerism wouldn't be present in alkanes.
Think about it. Alkane is just long carbon and hydrogen chain. Do you think metamerism is possible? Metamerism happens when on either side of a functional group, if the number of carbon atoms, like that's the only difference is there.
Oh, so we are not counting the functional group in this.
No. So if there's a difference in functional group, then that becomes functional group isomerism. No. Yahan pe functional group also is the same. It's the only difference in these two compounds.
Ma'am, I actually got kind of disconnected, but last thing I heard was about the metamodism part. Like you just started with it. So could you just repeat what you said?
Like revise it, Rishad, because metamerism is something we discussed in the previous chapter. Like can't repeat the whole thing again. But yeah, metamerism you wouldn't find in alkanes and hydrocarbons. In any hydrocarbon you won't find it. It's only with functional groups like ethers that you'd find metamerism. So the only type of structural isomerism you'd find with alkanes is chain, because they can differ in chain length. Position, because there can be they can have same chain length but differ in the position of the substituent, the methyl or ethyl or whatever they may have. Clear? So these are the only two types of isomerism, structural isomerism, that alkanes will show. Now coming to geometrical, like the stereoisomerism. What type of stereoisomerism can alkanes show?
The cis trans thing?
Cis trans, yeah, that is a type of stereoisomerism, but will alkanes show that?
No.
No, cis trans is not possible, but they can show optical isomerism. Not all of them, obviously, but some of them. Yeah.
Ma'am, when we were doing isomers, you actually stopped at geometric, so you didn't do optical. So could you explain what optical isomerism is?
So optical isomerism, the reason why it's called optical isomerism is because it relates to how that compound behaves with light, like when optical related to light, right? So organic compounds, they have a tendency to rotate light, rotate polarized light. Again, this is something related to property of light. So when I don't have,
Like the one thing you did is like we were showing markers and then you were rotating it in class or something.
yeah,
Like you had different color markers with views and
yeah, that is correct. Yeah, that will happen with tetrahedral structure also. That is correct. So compounds, like if you have a compound, let's say this is carbon atom, alkanes have sp3, matlab tetrahedral, right? So when you have 4 different groups attached on all 4 sides of the tetrahedron, so that I'm showing it with different colors here. So when you have all 4 different groups connected to a carbon atom, so this particular carbon atom, you say it is asymmetrical. It's usually shown with a star written over it. So the rotating light wala property is specialized only with asymmetrical carbon atoms. If by chance there is the same group attached on 2 of the sides, then it's not going to be asymmetrical anymore because there is symmetry created here. So that will not happen if there is like this asymmetricalness happens only if all 4 things connected to this carbon atom are different. So this kind of a carbon atom will have a tendency to rotate polarized light. Yeah. So they can rotate it, like if light hits them like this, they will rotate it either this side or this side. So depending on which side they rotate, that creates 2 different optical isomers. So you have something called like dextrorotation or levorotation. So these are like the 2 optical isomers. So one isomer will rotate to the right, the other isomer will rotate it to the left. So that's what optical isomerism is all about. Yeah, Rishit?
I didn't get it. Like, how does it become like symmetrical if you add it? How does it make it asymmetrical? Could you just repeat that part?
Yeah, asymmetrical is when you have like when all 4 groups attached to the carbon atom are different. That's the only criteria for it being asymmetrical. When you have completely different groups attached to all 4 of them. Like an example could be, if I have a carbon and yahan pe if I have a Cl, OH, H, and CH3. All 4 are different groups from each other. So this is an asymmetrical carbon. So there's like terms related to it. So this is called a chiral center and all. You don't have to worry about it. We'll go deeper into it in grade 12. Now, because I brought up optical isomerism, I just wanted to put in context what this means and why it is important. Just that, suppose you have asymmetrical carbon that has a tendency to rotate polarized light, and depending on the direction where it rotates the light, it can be either dextro or levo. So these are like the 2 optical isomers. So structure wise, it's the same because same group attached, same carbon, same chain length, same everything. The only place it differs is how it rotates this light, whether it's to the right or whether it's to the left. That is why they are isomers and they're optical isomers. Yeah. Now this is not a hydrocarbon, but hydrocarbons can show optical isomerism. Suppose you have a hydrogen here, CH3 here, C2H5 over here, and C3H7 over here. All these 4 groups are different, which makes this an asymmetrical carbon. So that's how this particular alkane shows optical isomerism. So I don't think any question will be asked on optical isomerism right now, but just in case you guys are aware of it, you know that, okay, this relates to optical isomerism. If at all you come across a question, let me know, I'll elaborate on this. But otherwise, it won't go like deeper.
I don't think, ma'am, this will come because our ma'am also did not teach us about this.
Yeah. Just so you're like familiar with the terms and have an idea that, oh yeah, this thing exists. That much is sufficient. Okay. So before we get to the properties, alkanes, they're made of only carbon and hydrogen, have only single bonds. Single bonds only. They're also called paraffins. Remember paraffin waxes? That's because they are made up of alkanes. The general formula is important to know, CnH2n plus 2, but that you're aware of since like grade 10. Hybridization important, sp3, that's why tetrahedral. Acha, carbon, so alkanes are made of carbon and hydrogen only, right? What is the type of bonding that you find? What type of bonds will you find between carbon and between carbon and hydrogen? Single bonds, yes, but what type of bond?
Sigma bonds.
Absolutely right. So between carbon or between carbon hydrogen?
Both will have only sigma bonds.
That is correct. So when you look at the bonding, the type of overlap in both cases, you find sigma bonds. No pi bonds here. All are only sigma bonds. So wherever there's carbon involved, you get sp3, and hydrogen, you only have that 1s orbital. Yeah. Yeah. IUPAC name, alkanes, kind of isomerism you show is chain and positional. Okay. And optical isomerism. Geometrical they don't show, but they show optical. Do you guys want to practice nomenclature a bit, or is it like too fresh? You guys can do it.
One to some
I could
questions.
practice.
I guess 2 questions or something just to.
A little bit, okay. All right. Practice nomenclature. Okay, I'm just gonna make up compounds and give it to you guys, okay? This is one. The second one, I'll give you guys bond line. So you guys can send it on chat and I'll look at it. Modifying the second one a bit, okay? Kaveri, first one, check the numbering. Rishit, yeah, you got it. Smera got it. Ritu, is that the first one?
Yes, ma'am.
Check your longest chain. There's a longer one. Kaveri, like you identified correctly, but remember, lowest possible numbering, position numbers.
Oh, okay.
Adit, check substituents for the second one. Sanad got the first one. Ritu, yes, now you got it. First is correct. Rishit, no, like longest chain you identified. Substituents, you mishmashed it somehow. So 2-methyl, you put it in bracket, that is fine. But if it's in bracket, it means that it's attached to something. What is it attached to? That also needs to come within the bracket. Kaveri, yeah, so your substituents and all, you identified it. Remember, when you're giving the name, it needs to be in alphabetical order.
Oh, yeah, sorry.
Smera got the second one correctly. Nice. Good. Ritu, no. Second one. Check it. No. Ritu, longest chain always takes precedence. Like when you don't. So if the longest chain, if you have multiple options for longest chain, but one is less complicated than the other, then you go for the less complicated one. Otherwise, go with the longest.
But shouldn't like the longest chain have like the functional group,
यहाँ पे
like the alkyl group?
here it's all alkyls only, no? If you have a functional group that's changing the alkene, like a double bond or alcohol or something else, then yes. But यहाँ पे it's all alkyl groups only. You just go with the longest. Rishit, yeah, now you got it. The second attempt is correct. Just that in brackets, check the numbering. So you count one if there's a branch chain, wherever the branch starts, that's where you count it. Adat, no. Why are the numbers alone in bracket? Like that's not how you write it. First one, pretty much everyone got it. I'm glad you guys counted it, checked the longest chain. So it's 1, 2, 3, 4, 5, 6 हो सकता है, but 5, 6, 7 heptane is longer, so this would be the chain. So substituents are you have and you have ethyl. Lower numbers are 2 and 4. You start from here, it's 4 and 6 higher numbers. 2, 4 is lower. If you go by alphabetical, you have 4 ethyl, then 2 methyl. Most of you got it. It's good. The second one.
Ma'am, so what exactly did you say I went wrong in?
Let me check again. Position number, like within the bracket, everything else is correct.
Does the numbering start from the branch inside or from where it is attached?
No, from the inside. Like whatever is the parent chain, these carbons are already counted. So you're already saying 4 or 3, like whatever position number is there, you're saying, okay, is carbon pe there is a branch. So within the branch, you start from whichever carbon it's attached from. So this would be carbon 1 and this would be carbon 2. Yeah. So if you want to describe position of this, you take this number. You missed out on the 1, Rishabh. Kaveri got it. Sanat, not really. All of you have identified longest chain possible. 4, 5, 6, 7, 8.
Is my first answer right or my second one right? Because I changed it a bit.
The most recent one that you sent. Yeah. Slight difference. Like you got all the words down. The formatting is not correct. I'll describe.
On 1 methyl or including 4 and ethyl?
I'll tell you like what, like you can compare the right answer, you'll get it. Octane is correct. Substituent 1, 2, 3 pe you have an ethyl group and 4 pe you have this whole thing. So, oh Kaveri, you mentioned methyl. Carbon 1, carbon 2, यहाँ पे ethyl होना चाहिए. So 3 ethyl. 4th position पे you have something really complicated, like branch के अंदर branch है. So start bracket. So you already have ethyl group attached to this at position 4. तो यहाँ पे आ जाएगा ethyl. Branch के अंदर, sorry bracket के अंदर, and ethyl के first carbon पे this is attached. So 1 methyl. Let me just write it again. So it is 3 ethyl. 4th carbon pe you have 1 methyl ethyl. Now all of these are attached to octane. So this is the final name. So when you have a branch inside of a branch, go logically. Don't try to form the name directly in your head. That will give you a lot of complications. So go logically. Longest chain you guys found out. Then see what all substituents are there. This is pretty simple. Ethyl hai. Yahan pe see what's going on. If you say propyl, if you have something like this, 1, 2, 3, this also can be a propyl. So how do you differentiate this propyl from this propyl? Again, IUPAC rules apply. Longest chain, 2 carbon atom long, but you're missing out on this. So how do you do that? Again, iska branch hai here. Now, because it's a branch within a branch and you're applying the same rules twice, whatever is inside the branch part of it will go in brackets. And this is the rest of the main name. It's very, very logical, guys. Like if you know the rules, you don't have to think further. Longest chain here octane. Octane के ऊपर 3rd carbon पे ethyl है, 4th carbon पे कुछ है. What is there? If it is simply an ethyl, it would have been 4 ethyl, so 3, 4 diethyl हो जाएगा. But it's not simply an ethyl. Ethyl के ऊपर 1 methyl is there. That's why you're putting it in brackets. ठीक है?
Ma'am,
Yeah.
is it necessary to write the 1 or is it like okay if we don't? If we only do the bracket?
Better to write it like. Just make it clear, okay, first carbon. Common name you can say for isopropyl also, like we'll come across that. Okay. Make sense? Kaveri, Sanat, Adit. Yes?
Yes, ma'am.
Okay.
Yes, ma'am.
Cool. So slightly complicated hydrocarbons nomenclature थोड़ा practice करना पड़ेगा. Okay, next. So before we go ahead with preparation properties and all, this is something you're already familiar with, but what are the different types of carbon you find in a hydrocarbon, in alkane usually? Okay. So you find like this is really, really important because again, as you saw in the previous chapter, in terms of stability, type of reaction, like what mechanism it's going to go through, all of that depends on this particular factor. This, like, what type of carbon is it? The first is it a primary carbon? Also denoted by 1 degree. Second is secondary carbon. That's 2 degree. Then you have tertiary carbon. Degree, and you have quaternary carbon. Are you familiar with this? Primary, secondary.
Yes, ma'am.
Yeah.
Yes.
ma'am.
Yeah. So just a quick revision. What is primary?
One is attached to the
Primary
center.
It's
carbon
bonded to one
attached
other
to
carbon.
Yeah, attached to only one other carbon atom. Secondary would be
2 other carbons.
Two other carbons.
yes. Tertiary,
3 other carbons.
Three other carbons.
Carbons for company.
quaternary.
4 other carbons.
Yeah, that's all 4 bonds are connected to carbon only. So when it's quaternary, this is when you get a neo situation. It's also called a neocarbon. So remember neopentane? So neopentane may you have this situation, remember? So this is called neopentane because it contains a neocarbon. All right. So once you guys tell me that you're ready, we'll start with the methods of preparation.
Ma'am, could you like go back to the slide where you actually wrote about all the the single alkanes? So that's like I
Yeah.
could not write that part.
Yes, let's take a break. It's 3:55, right? So 4 o'clock, I'll start with the preparation methods. Okay. Yeah, I'll be here. So just let me know when you want to note the next thing.
Ma'am, can you switch back to like this current slide we were on after research done with this?
Will do. Rishit, you done?
I've taken a screenshot, so I'll just write it now with the screenshot.
Okay. We'll meet back at 4. If there's anything you want me to switch to any other slide, I'll be here, so it's fine. All right, preparation methods, preparation of alkanes. So first method is you can prepare them from unsaturated hydrocarbons. What are unsaturated hydrocarbons?
Alkenes and alkynes.
Absolutely. For an example, I'll take alkene. So alkene, what is the structure?
CnH2n.
Formula name.
Like it has a double bond.
Double bond.
Correct. Unsaturated alkene, they're double and triple bonds. 4 more, it can be a long chain, it can be just as much, like whatever it may be. Basically, there is this thing. We're discussing preparation of alkanes, which means that reaction ke baad, we want it to be all single bonds. So how do we get from here to here? Like, what do you need to add, subtract, rearrange?
You need to add 2H2, right?
Correct. So we need to add a couple of hydrogens here, and then from an unsaturated hydrocarbon, you get a saturated hydrocarbon. So the reagent that you use in this preparation is directly hydrogen gas. Now, gas and gas reactions is really difficult to take place. So in this reaction, you always use a catalyst, which are either nickel or palladium or platinum. Okay, so these are the, like, this is the main basic reaction. You take a unsaturated hydrocarbon, make it react with hydrogen in the presence of a metal catalyst, specifically these three, any of these three, and then you get, like, just that the double bond changes into a single bond with hydrogen. Yeah.
Won't like the H2 be written on the left hand side instead of on the arrow?
Either way is fine. With organic reactions, it's like you can write it either way.
What does PT stand for? I forgot.
Platinum.
Okay.
So Ni is nickel. PD is palladium, like the mol. And PT is platinum, like the precious metal.
So basically this reaction is when there is a double bond of any unsaturated hydrocarbon, and we needed to make it to like alkanes. So we just need to add hydrogen.
Yeah, it's a hydrocarbon, right? Either you can add a carbon or you can add hydrogen only. The thing is, you directly add, in place of double bond, you add hydrogens and make it all a single bond.
Also, could you like once go to the previous slide?
Sure. This is the different types of carbons, primary, secondary.
Okay, ma'am.
Ma'am, I had a quick doubt. Is it like hydrogen and the metal, like either one of the metal, or hydrogen or the metal?
And or neck. Hydrogen is important because this is what is being added here. Now the metal aids in this reaction happening. So the how and all, I have a visual for it. I'll show it to you guys. For now, make a note of this. I'll talk about this reaction and then I'll show like how it takes place. So this particular type of reaction, like this is an addition reaction because you're literally adding a smaller molecule here. Specifically, the name of this reaction is hydrogenation. This is quite important. If you come across hydrogenation in any context, it just means that it is addition of hydrogen in the presence of this catalyst. It's an addition reaction where hydrogen is added to a compound in the presence of nickel, palladium, platinum. So if you, in like the context depends, like this particular hydrogenation, you're adding it to unsaturated hydrocarbons, but you also do that in preparation of alcohols and a lot of other contexts also. But yeah, in general, this type of reaction is called hydrogenation. This is the catalyst, quite important. The catalyst used is either nickel or palladium or platinum. One of these three, depending on cost, availability, like a lot of different factors. So the how of it in words, like if you have to know. So the metal adsorbs the gas. It's not absorbs, it is adsorbs. So adsorption is a different process from absorption. So it adsorbs H2 and it does something called, it activates the HH bond. Okay. Another important point is if you're using either palladium or platinum, so this happens at room temperature. But if you're using nickel, then you heat it at a slightly higher temperature. You heat it to either 200 to 300 degrees Celsius in order for this to work and work effectively.
Activates HH bond means?
Huh?
Activates HH bond means?
Activates means, in general, activation means it makes it like ready for reaction. So the whole process, once you guys are done noting these points, I will show the video of, what exactly is happening at a molecular level. So that way.
Ma'am, so I have a doubt.
Yeah.
So like if we were to use nickel instead of palladium or platinum, will we have to like heat the reaction?
Correct. You need to provide heat. So the process of adsorption and activating the bond and all of that will happen at 200, 300 degrees Celsius. But in the case of palladium platinum, it happens readily, like it happens at room temperature itself.
So
this
won't it be more like convenient to use palladium or platinum?
Yeah, but those metals, you also need to figure out the availability and the expense, right? So it's a trade-off.
Oh yeah, nickel is cheaper also.
Yeah. So if energy is more expensive and these are easily available, you go with this. But if sourcing the materials is more expensive, handling them is more expensive, but you have a bunch of coal or solar energy or whatever, then you go with this. So just whatever is convenient for you.
So the activate the HH bond means the one that we added like H2, right? Which we provide in the catalyst.
Correct. Yeah.
That is what that gets activated and then gets transferred to the alkane.
So any doubts regarding this point? Just wait till I show you the video of it. Because obviously it's difficult to describe in words looking at a screen, right? I'll show you the visual of how exactly this reaction takes place and what is the role of the catalyst. It'll make a little more sense. So let me know when you guys are done noting the whole, like all the important points here, then I'll show you the reaction. Okay, Adit is done. Smera is done. Bishop done.
Whole thing is called hydrogenation.
This reaction, yeah. So the addition, this is like in the previous chapter, we learned the types of reaction, right? You have substitution, you have addition, you have elimination, you have rearrangement. So that way, this particular reaction, because you're literally adding a molecule of hydrogen to the compound, comes under addition reaction. Specifically, because it is addition of hydrogen, it's called hydrogenation reaction. So hydrogenation reaction is defined as the reaction in which hydrogen is added to the substrate in the presence of the metal catalyst, nickel catalyst. Yeah. Cool. So everyone's done? Done? Okay. You guys can see the video clearly. Should I make it full screen? I haven't played it yet. You guys can see the screen clearly, right?
Yes,
Yes,
ma'am.
ma'am.
Okay. So this is the unsaturated hydrocarbon. Like the best way to figure out or identify
Audio.
no audio, no. So the best way to figure out or identify unsaturated hydrocarbon is your ghee, things like that have unsaturated, butter, all that have unsaturated hydrocarbons. The saturated ones are more like natural gas, oils, things like that, vegetable oils and things like that, right? So oily stuff, yellowish stuff. At the molecular level, you see that there is a double bond over here. So unsaturated hydrocarbon plus hydrogen, the presence of nickel catalyst, that is hydrogenation reaction. You can see exactly how it happens also. Hydrogen ke beech mein the bond breaks and that gets connected to carbon atom here. The double bond also breaks. Okay. So this is your structure of unsaturated hydrocarbon.
I don't know if it is for everyone, but the video for me is lagging a bit.
Okay. What I'll do is I'll play it here. I'll send you guys the link to this video also so that you can see it after the class. Okay. So step 1, adsorption of ethene and hydrogen molecules on the nickel surface. So this is important, and it's important not to get confused between absorption and adsorption. Okay. So first, what do you mean by absorption? Because that's something you guys are familiar with.
Something that like you take in.
To take, like, gain, absorb.
Can you guys give me an example? Like give me a visual or something where you find absorption.
Sponge absorbs water.
There you go. So when sponge absorbs water, like, can you describe that in detail for me? When you say absorbs, what exactly is happening there? So if this is the piece of,
The spaces of the sponge get filled with water molecules.
yeah. Any other thing, like, does it happen only on the surface, or is the whole sponge filling up with water? Like
Like it, holes are absorbing the water, like in the sponge ka material.
the whole thing is being absorbed with water. Is this a good representation of absorption?
Yes, ma'am.
Yes, ma'am.
Yeah. Now, when it comes to adsorption, AD, this happens only at the surface level. It happens only on the surface. It's a surface phenomenon. So absorption happens throughout the bulk. When it comes to adsorption, I'll do it over here. So if this, let's say this is like the metal surface. So adsorption, the whole thing is unchanged. Only on the surface of the metal, adsorption takes place only over here. Only on the surface. Okay. So absorption happens throughout, like sponge absorbing water. But when it comes to adsorption, it happens only on the surface. So other places you will find adsorption is like you have come across this in your real life. How do you get rid of smell in the fridge? Like, are you aware of that? That fridges over time, they tend to, like, you have food smell, you have the compressor ka smell, like there is some sort of a smell associated with inside the fridge, right? So what do you do to get rid of that smell? Do you have any idea?
No, ma'am.
Okay. Have you guys seen? Oh yeah, this is more relevant for you guys. You've heard of charcoal, right?
Yes, ma'am.
Yes.
Did you know that water is purified using charcoal?
Ma'am, your voice broke in between.
I've heard of it.
No, I was asking, do you know that water is purified with charcoal? Sometimes even alum is used. Do you guys know what is this alum? Alum, it's a type of crystal, white color.
Yes, ma'am.
So have you ever seen how water is purified using charcoal or alum or things like these?
Yes, ma'am.
How is it done?
Not like alum, but I did it as like a project in I think fourth grade where I put like cotton and like coal and sort of put water through it for like filtering.
Correct. Okay, but that's a project thing. So Ritu, okay, you've seen it. Rest of you are quiet. Like, is this something completely new to you guys? Haven't seen it, things like that, or
No, I've seen it, but like I'm not able to describe it in like words.
you don't have to describe the process because I know you might not be aware of it. But if you know that, in your house or in your grandparents' house or something, that it's a habit. Generally,
Like I've read about the water purification process in like I think eighth we had it in one of our science chapters, like the industrial water purification, one of these things.
right. And are you guys aware that when these things are used for water purification, it's not like a one-time thing, they are reused? Like they tend to be recycled. Okay, if you're not aware of it, like they can be reused. The reason is that in these processes, what is happening is that these substances, activated charcoal, alum, these things are basically absorbing the impurities from water. So like I've seen this in my grandparents' place. So at home, like we have a proper water purifier and all, but back when like almost 20 years ago or so, when I was a child, my grandparents used to do this. So they used to keep one block of alum in the fridge also. These days, you can also put baking soda in the fridge to get rid of smells. So the thing is, these solid things, they have the property of absorbing certain substances. It's not like they absorb everything.
I had doubt. So in our English textbook, if I'm not wrong, I don't know if it is also used in refrigerator, but they said to remove the smell, they burn sulfur. So is that also a way?
I am not aware of it. I know that if you burn sulfur, you get a really bad smell, like the rotten smell and all, suffocating thing, sulfur dioxide. I need more details on that, Rishabh. If you just say burn sulfur, it's not, I don't know.
Okay, I'll just send you that paragraph.
Later, yeah. But yeah, like things like these, if you put them in water, they absorb the impurities on the surface of it. They don't absorb it like sponge. These things just settle on the surface of it. Then you take it. Once you heat it, those gases, like whatever they absorb, that's going to escape out. And then you can like put it back in the water for purification. Yeah, so that's the absorption. Is basically you can think of it as a ferry service or something like that. It just sits on the surface. You take it, you clean it up by heating it or whatever, and then all of those things escape, and then you can use it back for purification. Yeah, so that's like one of the main differences between absorption and adsorption. So you can see So those are like some physical everyday life kind of examples that I gave you guys. Adsorption also happens in chemical processes and reactions and all, and you will see it in the context of hydrogenation, what happens here. So you have ethene molecule. So the gray thing is nickel metal. Just like metal, it's a solid. All of the molecules are regularly arranged. You can see that the ethene molecules are just settling on the surface of nickel, the metal block, the solid metal. So adsorption, because each individual molecule is settling on the surface, it just makes more molecules available for reaction. So it increases the concentration of ethene on the surface of catalyst. More concentration means more molecules available for reaction. So that in turn increases the rate of the reaction. Like, think of it as when you're drying a cloth, crumpling it up versus spreading it out. So using a catalyst basically spreads out the whole of these things.
Ma'am, so seeing this, I had a doubt. So, if we know the catalyst makes the hydrogen, basically the hydrogen gets separated and then attaches with the alkane. So, what exactly makes, so if the catalyst is just left alone, will nothing happen? They just need something to get activated.
No, it's just the catalyst plus the reactant getting together is making this. If you have nickel and nothing else, then nothing is going to happen. Because you have nickel, and then you're like glowing, like putting your hydrogen gas, your ethene gas over nickel, you can see here. So nickel, because of its electronic structure, it's got empty orbitals and all, it forms these slightly weaker temporary bonds over this. Like, this is what makes adsorption happen. The reason why these gas molecules stick to the surface of the metal is because you have these weak sort of bonds taking place between the gas molecule and nickel. Yeah. Similarly, hydrogen also settles here, breaks the bond between hydrogen, and each hydrogen atom basically like forms a newer bond with the nickel itself. So if you have hydrogen and ethene close to each other, the whole system, like the carbon and the hydrogen, are much happier forming the bond with themselves. Yeah. So ethene is like, okay, these electrons are like, instead of settling with weak bond, let me form this stronger bond which will fulfill the octet and everything. So it, bonds with carbon like this. So this way. So step one, because you're exposing ethene and hydrogen to nickel, adsorption happens. Adsorption is nothing but it activates the HH bond. It breaks the bond between the hydrogen atoms, and then each atom individually forms a bond with nickel. Now this is not like a full-fledged chemical bond. It's not like a single bond or a double bond or something like that. It's a weak sort of bond. Think of it as nickel has empty orbitals. Okay, these hydrogen atom have single electron. Okay, so those electrons, while roaming, they're like, maybe they get into the empty orbital of nickel. It's just, think of it as van der Waals attraction maybe. It's a really weak bond. It's like very temporary. Now, when a lot of that is happening, so you have an ethene molecule nearby and the hydrogen atom over here. Both of them have weak bonds to nickel, but the interaction between them, it's like, if there is a bond forming between the carbon and this hydrogen, this is like a much stronger, better bond because there is octet being fulfilled for this carbon and for the hydrogen as well. This is like a much better deal for, the atoms and their electrons. So rather than sticking to nickel itself, they're like, hey, let's form a bond with each other. So that's what happens with another hydrogen atom also over here. You can see the bond is in the process of forming between both of them. And once, initially it was like this, but this bond broke as it was being adsorbed on the nickel surface. And then hydrogen also was there. And then eventually it formed bond individually with hydrogen. So this is what happened during the reaction. This is how hydrogenation has taken place. Yeah.
Adsorption will break the HH, like activate the HH bond. That what is the meaning of that? I still didn't understand that.
Makes it ready or prepared for the reaction essentially. Like you can see that because the hydrogen atom, instead of it being a molecule, it partially weakened this bond by making the electrons get attracted to the nickel block. So once this bond is broken, this hydrogen is like ready for reaction. It's like activated.
But when were the hydrogens together in the first place? It was always like CH, right? So how did the HH bond get activated?
This is the new hydrogen. It was never CH. CH happened newly after the reaction. So you have C double bond C and you have H single bond H. These two are reacting. Now this bond got activated by this bond gets weaker, this bond gets broken, and then these electrons, like these two, form a bond with each other. And that's how you get all single bond with new hydrogen atoms attached.
So the bond between the carbons is weakened because of?
During this reaction, like as it gets absorbed on nickel catalyst. The hydrogen also bond breaks, gets closer. They're like, hey, this is a much better deal. Like, let's just form a bond with hydrogen here. That's what reaction is, right? Like rearrangement of the bonds, forming new products.
So basically, after adsorption, the HH bond breaks and the CC bond also breaks, and then the CH and then CH and CH combine.
Correct.
Okay.
Yeah, I'll send this video link to you guys so you guys can see it not as a slideshow, like you can see it properly.
Ma'am, I know it's a bit too late to ask, but the hydrogens come basically from the nickel.
How is the hydrogen coming from nickel? They're all three different things. You're putting them together so that the reaction can happen.
Yes, but where exactly does the two hydrogen come from? Because in the video it just showed it came from the nickel side. Just got confused in that.
Oh, that's another reactant. You are making this reaction happen so that you can prepare ethane. So this whole thing is like, this is a factory. You have unsaturated hydrocarbon here. You put nickel also over here, and then you can diffuse the raw materials from this tank. So you're diffusing these hydrogen molecules through this. So you are putting together all these three things, and then the reaction happens because all of them happen to be together, and temperature, pressure conditions happen to be all right for the bonds to break and the bonds to form. Okay. Okay, so this is the first method of preparation, guys. So hydrogenation reaction, bottom line, you take an unsaturated hydrocarbon, you pass hydrogen gas like through it in the presence of catalyst, turns into an alkane. So the double bond breaks and hydrogen is added to it. So
Is
extension
this method called something?
hydrogenation. Okay, I'm assuming that you guys have noted all of this down.
Yes,
Yeah,
ma'am.
yeah.
Okay. Unsaturated, right now the example that I showed you guys was with alkane. Now what if I took an alkyne? What is the difference between if I had to prepare ethane from ethyne? Will everything remain the same or is there going to be any difference? Fill in the blank, like what reagent?
We need more hydrogen.
Absolutely.
To add
Yes. So instead of a single molecule of hydrogen, you need 2 molecules of hydrogen because, you know, you break one bond, you add 1 molecule, becomes an alkene. When you break the second one, add another molecule of hydrogen, becomes an alkane. The reagent, everything else remains the same. Use a catalyst, just that you need to use more hydrogen because there's more bonds to be broken. But the principle or the mechanism or the whole funda behind it is the same. Just a little more additional effort because instead of a double bond, you have a triple bond. In order to make it a single bond, you need to take off 2 other bonds. That is the only difference. Everything else is the same. Okay.
Yes, ma'am.
Cool. Next method of preparation, using alkyl halides. Do you remember what alkyl halides are? Give me like a general formula or something to represent alkyl halides.
XCH3 where X
CH3Cl.
can be a highlight.
There you go. So any alkyl group plus halide X, where X can be either a chlorine, it's a chlorine atom or fluorine or bromine or iodine. Yeah, any halogen. So in order to
I don't think they include fluorine, right?
yeah, usually fluorine reactions
Because it's too reactive.
yeah, they're explosive, gets violent, difficult to control. So
And
usually
they don't include iodine because like it's reversible, right?
that depends on what reagent you're taking, under what conditions and all of that. So those finer details are there, but in general, this is the format for alkyl halides. Yeah, so we'll touch upon that. So you take an anyway, take an alkyl halide. We are preparing an alkane. So essentially, what is happening in the reaction? Like, what's your aim? If you're starting off with an alkyl halide, what do you need to do to get an alkane out of it?
Replace the halogen with hydrogen.
Correct. You need to take away the halogen, replace it with a hydrogen. So there are a lot of ways to do this. So the first way to do it is one, direct reduction. So reduction reaction, addition of hydrogen. So you're literally adding an extra hydrogen here in place of the halogen here. So reduction, there are a couple of reagents you can use. One is you can use an acid in the presence of zinc. Remember, if you put zinc in the presence of acid, zinc will displace hydrogen from that. So usually in this process, dilute HCl is used. So that is one source of hydrogen here. Another reagent that is used is red phosphorus in the presence of hydrogen iodide, Hi. Okay. So this is used usually for iodides because, like, if you look at it, it's basically a substitution reaction, right? So you're putting the hydrogen in the hydrocarbon, like to make the hydrocarbon, and then the iodine and iodine combine to form I2 gas, and that I2 gas is removed by the red phosphorus. Okay, so this is the other reagent used in this process. And so basically the red phosphorus reacts with iodine gas. In this reaction, you get the product Pi3, and this is volatile, like it is pretty volatile. It can escape as a gas. So if you're removing the product, then, you know, if you don't have any iodine, it will not have a chance to react and, you know, reverse the reaction. So that is the reason this particular red phosphorus is used if you're using HI in this reaction. So we'll do a couple of example reactions once you're done noting the important points.
Could you go back?
Okay, not done yet. So,
Ma'am, 1 minute.
not done. Yeah.
Ma'am, just what is red P and HI?
Red P is phosphorus. So red P is red phosphorus. So phosphorus has two allotropes, like you have white phosphorus and you have red phosphorus. And then you have like violet phosphorus, black phosphorus, but they are at very high temperature. These are like the common ones that you come across. White phosphorus is the one that explodes, like lights up spontaneously. Like you put it in water, or you just put it, like just do this in air and then it catches fire. Red phosphorus is the one you find on matchsticks. So just with small spark, like with that the friction produces, it lights up. So that's why red phosphorus is used in matchsticks. So it's just one form of phosphorus, like the way carbon exists as diamond, graphite, and all of these, right? That way phosphorus, white phosphorus is one allotrope, red phosphorus is one allotrope. Here you specifically use red phosphorus. HI is like HCl, HI, hydrogen iodide. Okay. So for example, let's say you have CH3Cl. If I treat it with Zn and HCl, what is the product that will be formed?
CH4 and Cl2.
Methane and hydrogen.
Technically, instead of Cl2, you would see it in the form of ZnCl2. But yeah, this is like not important. The main thing, focus on the fact that if you have an alkyl halide, and sometimes you may be given HCl directly, sometimes you may be given as H plus and Zn. Basically, zinc in acidic medium, you get alkane. Okay. Similarly, the other reagent that we discussed, let's say you have ethyl iodide, C2H5I. If I treat it with HI in the presence of red phosphorus, predict the products here.
C2H6 plus 2I.
There you go. 2I? How does iodine exist, elemental iodine?
I gas, like I2.
I2, yeah. So this I2 that is produced reacts, like the red phosphorus reacts with this, and it is removed as PI3. Phosphorus iodide.
Ma'am, I actually didn't get how to do this.
What do you mean? How to do this in the sense?
How exactly we are doing like C2H6 plus I, or even the CH4 plus ZnCl2, I can still see how it is. But for this one, C2H5I, and like basically this method I could not understand, the alkyl halide one.
See, these are all preparations of alkanes. So the questions like how you need to remember these reactions is, rather than remember every single product here, remember it again. Going back to our previous chapter, remember the substrate, reagent, and product. So substrate, the way I'm taking you guys through the, what do you call, this whole section, any reaction for that matter, this is how I'm going to do it, okay? Substrate, in the first case, we're looking at unsaturated hydrocarbons. So if we were to get an alkane from unsaturated hydrocarbon, what all reagents can we use? In this case, it is hydrogen gas directly. This is the only thing. The next one, substrate is alkyl halides in all the cases. What all are the different reagents you can use to get an alkane? One is Zn in the presence of acidic, like Zn in presence of acid, usually dilute HCl. Another reagent is red phosphorus or HI in the presence of red phosphorus. So this particular method is usually used for iodides. The reason why you prefer it for iodides is so that you can remove the iodine that is produced. Okay, because if you don't use the red phosphorus, this iodine is going to react with the ethane, whatever alkane is produced, and then you're not going to get your alkane. You'll be left with this only again. We don't want that. We want to prepare this. Yeah. And I would suggest whenever you study reactions in any organic chemistry chapter, study it in this way. For a specific substrate and a reagent, what sort of product you're going to get? Because the questions that you'll be asked for reactions is either you'll be given these two and then you'll be asked for the product, or you'll be given the substrate and be like, oh, if we want to produce an alkane from this, then what reagent is suitable? Or you'll be given slightly, detective kind of questions, like a substance X with the molecular formula C4H9Cl was reacted with a certain reagent, and this is the product that is formed, then identify this. Okay, so typically the questions you'll be asked, especially because now you guys are doing MCQ, is you'll be given 2 out of these 3 and you'll be asked for the third one. So be familiar with, for this particular substrate, if we use reagent A, this is going to be a product A. For reagent B, I'll get product B. For reagent C, I'll get product C. Okay, so in some cases, you'll be given the mechanism, pay special attention to the mechanism. Otherwise, other cases like these, it's fairly logical. If I'm given an alkyl halide, treat it with acid ka defining thing is H+. So H+ is going to take the place of whatever halide that is there. So I'm going to get an alkane. If I treat it with HI in the presence of red phosphorus is there to take away the iodine. So you can figure out that, oh, if iodine is gone, then the remaining hydrogen is going to be substituted over here. Okay. So you can like think of it, you can like remember or form patterns that way. Yeah.
Then just the first one again, first reaction.
This one. So alkyl halide, so chlorides treated with zinc in the presence of an acid. Again, you guys need to have sense that HCl is an acid, like that produces H+. And it's not necessary that you'll be given HCl only. Instead of HCl, even if you're given H+, just see the combination of zinc plus H+ and be like, oh, it is reduction reaction. H+, the hydrogen substitutes the chlorine. So this is a method of preparation for alkane.
So ma'am, the H+ that you've written under the arrow, like as plus H+, because that's not exactly like a catalyst, but we're like adding those together.
I'm just like, again, as I told you, all the reactions will study it as substrate, reagent, product. So the important point you need to get from this reagent is that zinc in the presence of acid. Usually the acid is dilute HCl, but I also mentioned H+ because if you're not given HCl, don't be confused. You're using HCl for the purposes of H+ over here. You may be given as zinc and H+. You may be given as zinc or HCl. Either way, it's the same thing. It is a reaction between alkyl halide with zinc in acidic medium. So you're going to get an alkane.
If we are given only H+, will the equation be CH4 plus ZnCl, or will the Cl2 still exist because it's in the elemental state?
Then that's not a reaction at all. You're just putting an alkyl halide in an acid. You need zinc for this reaction to take place.
No, zinc is there.
Oh.
But instead of HCl, only H+ is there.
Same thing. Like, that's why usually this part is also like ignored. That is why focus on the substrate, which is alkyl halide, reagent taken, which is zinc in HCl, and the product form, which is alkane. These are the things, main characters you need to focus on in organic reactions. Substrate, reagent, and the product. In this case, I also mentioned I2 because there is a special note, like the whole reason why we're taking red phosphorus in our reagent is to remove the I2. So unless there's like a special note or some sort of importance of a specific reagent, you don't have to care about it. Yeah, Kaveri.
The red P is used to remove the iodine as Pi3 that I understood. But then what is the use of the HI there?
HI is the one that's giving hydrogen so that you get your alkane, which is the hero of our story. The whole reason why we're studying the reaction is so we can prepare this.
So do we not need an acidic medium there?
No. So in terms of acidity, HI is more acidic than HCl. And both the reactions are different, right? Like this in an acidic medium follows a different mechanism compared to this. They're both different reagents that we take.
So we can write like red P in the presence of red P and HI, which can be used as an acidic medium. We get C2H6 plus Pi3.
Don't add all of those words. Reagent red P plus HI, you get C2H6. That's it.
Okay.
And remember, you're doing MCQs. There is like specific reason or something like that. I will mention it. Otherwise, just focus on what is the substrate, what reagent is used, what product is formed. Just use this format to learn the reactions.
And instead of writing removed as Pi3, can't we just simply say C2H6 plus Pi3?
I had mentioned this because, again, if you get a, let's say, assertion reason question about the presence of red phosphorus, or presence of red phosphorus, so it can react with I2 and you can remove this as Pi3. Can I add one more point? Why should we care about Pi3 is because this is a volatile compound. It can just evaporate off as a gas. As I said, like if there's special notes like these, I will mention it. Otherwise, know what is a substrate, what is a reagent, what product we make. 3 main characters in our story. Okay. This is one way of doing it. With alkyl halides itself, this is A, reduction. B, again, this is an important because it's a named reaction. This is called Wood's reaction. Woods is the name of the scientist who must have worked on this. Pay special attention to named reactions. We'll have quite a few of those in the whole of organic chemistry. Especially Wood's reaction, we'll come across this in grade 12 also. Here we're studying it as preparation of alkanes. There you'll study it as a chemical property of alkyl halide. Same thing. So that's why. Yeah. What's up?
C2H5 reaction. We don't need anything zinc or anything, right? Just...
No. Iodide, red phosphorus. Hydrogen iodide, red phosphorus.
So, apart from iodide, all the other ones need zinc, or or others also include in this exception?
Usually chlorides, if you like use zinc in acidic presence.
So how would we know which thing?
See, Kavil, this is like different ways. Again, always comes back to substrate reagent product. If your substrate is an alkyl halide, Rx, this is one reagent that you're using. So this way you get direct alkane where the halogen is directly substituted with hydrogen. So one reagent you use is zinc in the presence of HCl or acidic medium, basically H+. Another reagent, like if you're looking at iodide specifically, then you use HI in the presence of red phosphorus. Again, it's not completely black and white because these are preparation methods, right? there would be infinite methods of preparing a particular compound, but you also have to look at the economic viability, feasibility of it. You don't have infinite energy or resources. So these are the reagents that have been found to be most efficient and easy to do it. Like in some cases, rate of reactions will be low. In some cases, it's going to be violent, which is why you won't come across any fluorides here, even though we say alkyl halide. So usually you take chlorides, bromides, iodide. If it's a chloride, you take zinc HCl. If it's an iodide, this is the most convenient way to prepare it. Okay.
Ma'am, halides are basically halogen plus any element, right?
Compounds of halogens, yes, halide like the X minus or these kind of things. Now, even in Wood's reaction, you start off with an alkyl halide, Rx, but the product and the reagent vary in this case. So here, you take sodium metal in the presence of dry ether. The product that you get is double of what you start off with. RR plus X2. Okay. In this case, you started off with one carbon atom. Your product also has one carbon atom. In Wood's reaction, you start off with whatever X number of carbon atoms. Your final product is going to have 2x number of carbon atoms. Like for example, if I take the same CH3Cl, but instead of ZnHCl or whatever, I treat it with sodium in dry ether. Then I'm going to get CH3CH3 plus Cl2. So I started off with one carbon atom. I ended up with two carbon atom product. Methyl halide gave me ethane. So same substrate, but with this particular reagent, I'm getting a different product. That's why this is a different, we are learning it as a different reaction. Okay?
What happened to
What happened with what?
what happened to the Na?
Oh, I'm sorry. It won't be X2 here. It'll be 2NaX. So we get NaCl. Again, as I said, focus on substrate, reagent, and the main product. So here again, when it comes to reagent, it's not just the Na. Pay special focus on this also, like dry ether is important, because if there's like any sort of a moisture involved, then it's going to be a completely different reaction. You're going to have OH substituting in place of, these two connecting with each other. You're going to get a completely different product. So Wood's reaction reagent is sodium in dry ether. You need to have a non-polar environment for this reaction to take place. So once you noted this, we'll go through a couple more cases of this reaction. Also, because these reactions are going to follow you throughout, even in 12th grade, I would suggest maintain like a separate chart or a notebook or something in this format, like substrate, reagent, product. Because a lot of times the same reactions will repeat again in a different context. Like here you're learning it because it's a preparation method of RR. Next year you will learn it as a property of Rx. Like you take an alkyl halide, make it react with this, you're going to get an alkyl. So just learn these independently as reactions and group them as, okay, so and so substrate plus so and so reagent, I'll get so and so product. So that you can make like a mind map, like a chart out of it yourself. It'll be easy to check back and revise when you come across it again. The others is the only one done. Rest of you still noting it down or what?
I'm on the last part now.
Ma'am, this is like a small doubt. So when we say R or Rx or RH, the R itself is only the hydrocarbon, right? Or does it also contain the functional group?
No, alkyl. R means alkyl. Only the
Only alkyl. Okay.
minus one hydrogen, like minus one bond. That's why R, and then always connected to X or H or something else. Cool. I'll ask this as a question format. So suppose I'm using sodium in dry ether and I want to produce this compound. What raw material should I take?
Propane.
Propane chloride. Propyl chloride, sorry.
So Kaveri, if I'm already taking propane, I'm like, this reaction is not going to happen. What's this, like we're still in alkyl halides. So Ritu, yes, propyl chloride, but again, remember there are isomers to it. So will I get my required product with this or this? A or B?
B.
Kaveri, Smera, Sanat, Rishit,
I
Adit.
didn't get what we did.
Have you guys written the reaction, like the general reaction here?
Oh, I wrote that.
Yeah.
So observe that, like see what is happening in the reaction and apply it to the compounds that are here. So I told you this is the product that we need. What is the raw material that I have to take? The reagent I'm taking is sodium and dry ether.
B.
Okay.
Wait, what do we need to do for the B?
No, like I'm asking the question, what is the raw material, A or B? These are the options. What should I take here out of these two? I'll give you guys a hint. Like the previous reaction that.
Take B.
Okay.
I do think it's B.
I took 2 molecules of this, treated it with sodium in the presence of dry ether. I got CH3 single bond CH3. So this is what we studied. Take an alkyl halide, sodium and dry ether. I get double of whatever I took earlier. So using, like see what is happening in this reaction here and then apply it to this. So here I've given the product.
B.
B.
Awesome. Very good. So good. So what's happening is cut the bond at wherever the halogen is and then join the remaining parts together. So here you can see that like it's double of whatever, right? So figure out where is the symmetry here. So if I cut it over here, I'm getting like 2 identical compounds here, right? Which means that there must be a halogen over here in the center, CH3CH, halogen and CH3, which happens to be B. Yeah, so this is how your organic reaction-based questions are going to be. In this case, I gave reagent and product here to figure out the raw material. Okay. Easier direct question would have been whatever we did earlier here. You'll be given, okay, methyl chloride here, treat it with sodium and dry ether, then what will I get? Okay, so these are the kind of questions you'll be getting. So follow the logic behind the reaction, like what's happening here, and then it'll get easier. Then you can figure out the answer. Okay. I'll give you another case. Can I produce methane from this method?
Methane is CH4, right?
Yes.
No, you can't. Because like you mean like can we get methane in the product side, right?
Yeah. Can I use?
No, we can't.
To produce methane?
We can't because like
I
in the
don't
product
think.
side we'd always have like double of the I forgot the name.
Yeah, double the number of carbon atoms.
Substrate.
Carbon.
Yeah.
It's alkyl.
Correct. So this is not suitable for producing methane. You have to write it more formally. You can say not suitable for producing methane, this particular method. Yeah. Okay. I've taken single reactant here. Like I've just taken methyl chloride, propyl chloride, ethyl, whatever. What if I take 2 different types of halogens? Let's say I take CH3Cl plus C2H5Cl. Give it the same treatment. Sodium in the presence of dry ether. What product will I get?
Just a small doubt. Will we get 2 products? Or only one?
Good point, Rishad. What do you think?
Maybe 2. I'm not sure.
Think of it like follow our logic. If your logic is right, you should be confident of your answer. Okay, Rishad has followed some logic. Like, what do the rest of you think? What's your answer?
I also
There are
think
two
that there would be
products,
like
won't
2
we-
products.
Won't we need like 2 Na?
Yeah. Like, imagine you obviously won't take.
Can one product be 2 NaCl?
Hmm?
Can one product be 2 NaCl?
That's not what we want to focus on, Adit. Like, our reagents are hydrocarbon, like organic compounds, right? So what organic product are we going to get? That's the main thing. Smera
I think that
yeah, Ritu?
you'd get like one organic product where like the methyl is doubled and a second one where like the ethyl is doubled and then like the NaCl.
Okay. You guys are very close, but you're still not looking at the bigger picture here. You guys are right, but keep an open mind. Okay. So the funda of the reaction is that the halogen breaks off in each case. In every single molecule, the halogen is breaking off. And whatever alkyl groups are remaining, that joins in, right? So imagine like all these reactions, we do reactions in a vessel, in a beaker. And it's not like single molecule, like these are atoms and molecules. It's not a factory assembly line. And when I shake a reaction vessel, all these atoms and molecules bump into each other at random. So one possibility is that two of the methyl groups can bump into each other. So you get CH3, CH3. Two of the ethyl groups can bump into each other. So you get C2H5, C2H5. One of this can bump into one of this. So you can also get CH3, C2H5, the C3H8. So these are all the possible products if you take two different alkyl halides. Okay. Kaveri, C3H8, C3H8 will not be a possibility because it needs to be an alkyl halide because, you know, that's where the halogen is breaking off and that's the source of the alkyl part. If I have C3H8, that doesn't have any halogen there, so that's not going to take part in the reaction.
No, in the product.
Yeah. So this is C3H8, right? It's not C3H7Cl. It's directly C3H8. You won't get C3H8, C3H8. You won't get hexane out of this.
Why not?
I just told you, you need to have propyl halide in order to get hexane. You need to have C3H7Cl. Then this bond breaks and you can have two of these C3H7 with each other. But you don't have this, right? Like, what is the source for this? You just have methyl chloride and ethyl chloride. You don't have propyl chloride here.
But if you're saying there are different possibilities, then this can also be a possibility.
If you take propyl chloride, but that's not here. It's not present. Where did you get it from?
Adding the carbons and the hydrogens.
Where are you adding it from? In my reactant, I just took this and this.
Yeah, so CH3 and then the C and C2. So that becomes C3 and then the H3 and H5 that can become H8.
Yeah, this is a possibility. This is a product.
Yeah, so that's what I wrote.
No, you wrote the second one that you wrote.
Yeah, so doesn't that become double then, like RR?
Okay, two mistakes here. Because one, C3H8 is this. 3 carbons, you have 8 hydrogens. That's it. This is the complete compound. If you write it as C3H8 bond C3H8, यहाँ पे बीच में 2 of these carbons are having 5 bonds, which does not make sense. And 2, you need Rx in order to get the RR. This is just a complete alkane. You need to have C3H7Cl. Then it becomes part of the possibility. But this is not there in the reactant.
Ma'am, a small doubt.
Hmm?
How did you, I don't know if you wrote it just because it is there, but how did you get C2H6 and C2H5? Is it because you doubled CH3?
No, this is C2H5, C2H5, not C2H6.
How did you even get, how did you like get the both possibilities together?
4, 9, only 3 possibilities.
No, like C2H5 and C2H5. How did you get those two?
Because I have C2H5Cl. One of this bumps into another of C2H5, I get C2H5 bond C2H5.
Oh, ma'am, I had a question.
Isn't it
Like,
same
not
for the CH3?
Yeah.
Like CH3 or something like. Oh, okay. All
I have
right.
this, and then have if one of this bumps into one of this. Yeah, that what's up?
I just want to like just like it's like the CH3 over here is like the general formula you can say here is like 2n plus 1 is if C is 1 and then H3 is like 2n plus 1. Then similarly C2H5 is also the same way.
Yeah, because they're all alkyl groups. They're not complete alkanes. So it's the alkyl groups that are joining with each other. So essentially, like if I had to animate it and show it to you guys, this is what is happening. From this compound, this breaks off into CH3. This breaks off into C2H5, like the halide has broken off. Now, whenever you do these reactions, you're not going to take single molecule, right? There's going to be like 10 power 22, 10 power 23, like billion, trillions of molecules. So you'll have a whole bunch of, these in the solution. So it's a matter of what bumps into what. If this bumps into this, these two together, you get this particular thing. C3H8, 3 plus 5, 8. If this bumps into this, CH3, you get ethene, C2H6. And if this bumps into this, you get C2H5, C2H5. I can say, okay, this is bumping into this, same as the C3H8 only. So you need to look at permutations and combinations between whatever is available in the reaction vessel, which is an alkyl, a methyl group and an ethyl group. That's why these are the 3 possibilities you get.
But I still didn't get how can CH3 bump with CH3 itself? Like that part I didn't get.
Why not? Imagine like your reaction vessel, your beakers and test tubes are going to look like this. Will you control what molecule bumps into what molecule? Like, can you control at the molecular stage in this case? It's a reaction vessel. Anything can bump into anything else. All of these are there in the same vessel. That is why these are the possibilities.
Ma'am, then we have to have like RR, right?
Have to. That's the general thing. Like, so the general formula for this is if you take two different, you take Rx and R dash X. So Na in dry ether, this particular reaction, either you get RR where the same thing bumps into each other, or R dash. So again, same thing of the other thing bumping into each other, or one of this bumping into one of this, which is R dash. So all these 3 are the products. Correct?
So
Simple. Like once you get the hang of it, take away the X part of it, and whatever is remaining, just join them all, like R dash, or R dash. And the more,
so instead of R getting doubled, we can just like find different permutations of combining R with R, then R with R dash, and so on.
yeah,
And then we have only like the NaCl will be only one, right?
yeah, any like whatever halide you take here, it'll just join up with that.
Would we need 2 NAs for this?
Yeah, I mean, even if I write Na here, that doesn't mean I'm going to take a singular Na.
Yeah, I'm just asking.
Yeah, you balance it out based on how many ever R dash you have. That's it. So these are like the main things related to Wood's reaction. So just summarizing it, this is the main thing. You take an alkyl halide, sodium, dry ether. Dry ether is quite important. The mechanism is that you eliminate, like the halogen part of it is removed, and whatever alkyl part you have, that joins them together with each other. So depending on what you take here, that will decide what products you get. If you take the same kind of alkyl halide, you're going to get double of that thing, which is what we saw in all of these cases, right? I take methyl, I get ethyl. I take ethyl, I get butyl. If I take a 3 carbon atom thing, that same thing just gets doubled. And if I take different alkyl groups here, then depending on what I take here, the kind of products I get just changes based on that. So you just have to focus on, like if you see sodium in dry ether, simply look at what is the alkyl part you have, just join them all together to get the final thing. Okay?
Ma'am, so just small doubt. So CH3 and C2Hy, now when they combine, we get C3H8. So that is itself the product, or that too gets doubled?
No, that itself is the product. This is a product you're getting from these two reactants, no?
Okay.
Yeah. Okay, so that is Wood's reaction. And another reaction that you use alkyl halides in is with Grignard reagent. Grignard reagent is very, very, very important. You keep meeting this particular thing again and again and again, a lot of times. So Grignard reagent in general, okay, first I'll tell you what it is. So you will never find this independently because it is extremely reactive. It's very unstable. So you always prepare Grignard reagent freshly when you want to do that reaction involving this. The reagent itself is RMgX. So you can see why it's very, very unstable, because you're taking something that likes covalent bonds, like carbon-based thing, and you're mixing it with something completely ionic, like metal, like magnesium metal. So because of the difference in polarity, difference in properties here, this bond can break very, very, very easily at the slightest of, like even if you have moisture in air, this is going to break and, you know, form alkane and hydroxide over here. It's that sensitive. So usually, because you can break this easily, you use Grignard reagent wherever you need to add an R. Like here, preparing alkanes, it's all just R and then hydrogen, right? It's just hydrogen and carbon. So if you want to increase the chain length in an alcohol or something like that, wherever you need to add the R part of it, you use Grignard reagent. Okay. So how do you prepare Grignard reagent? The preparation of Grignard reagent is you take alkyl halide. If instead of sodium in the previous case, you take magnesium in dry ether, you get Grignard reagent. Basically, magnesium glucosifies itself between R and X. That's it. And because this is very, very volatile, so you take Grignard reagent like RMgX, put it in the presence of a proton. So proton is any, like even if you have the slightest hint of H plus. So it doesn't even have to be acidic. Even if you put it in the presence of water or ammonia, which are not necessarily acidic, but compared to Grignard reagent, they definitely are. Like this has a tendency to separate out the hydrogen from the others. And you get an alkane. Any source of proton. So for example, if I take CH3 MgI plus water. So I'll get CH4 and MgOHI.
So ma'am, like where do we use this reagent?
So to prepare alkanes in this context. And then as I said, you'll keep coming across it. Usually you'll come across it wherever you need to add this R. So this is very, very reactive. You can think of it, it's like extremely basic. It doesn't have to be water. Like suppose you can even use alcohol. Like if I take ethyl alcohol, it is capable of pulling the proton from ethyl alcohol also. So you end up getting this plus Mg, C2H5O and I. So any compound that has a positively charged hydrogen, like in alcohol, because this hydrogen is connected to oxygen, like remember, this is polar, like oxygen being electronegative, hydrogen being electropositive, like it pulls the electrons. H has a slight positive charge. That itself is enough to, for the MgI to take away this thing, and H gets attached to the R part of it.
Ma'am, I have a doubt. So basically, the first one which you wrote, like preparation with alkyl halide. Wait, sorry, no, preparation is not there. Alkyl halide plus Mg by dry ether and R. So is that different from the one which you wrote?
Yes, of Grignard reagent. So once you prepare this Grignard reagent, you can use Grignard reagent, treat it with any H plus source like water, even alcohol is like, usually you won't associate alcohol as being acidic, or you don't use alcohol for getting H plus out of it. But compared to Grignard reagent, this is powerful enough to break this bond. So any slightest source of, hydrogen that is attached to an electronegative atom, that is sufficient for Grignard reagent to want to produce an alkane. So one thing to remember is that if you're using Grignard reagent, you get an alkane out of whatever is attached to the Grignard reagent. like you can see in this example, even though I took C2H5OH, I didn't get ethane. I got methane because it is CH3 that is attached over here. So another example. Okay, can you predict the products formed from this? Are you guys still writing notes, or are you stuck, or what's going on?
Will it be something like this? I am not sure, but a C2H6 plus MgH2O water plus iodine. Will it be something like that?
Give me the main product, like what alkane will be produced from this. Are you going to get benzene, or are you going to get ethene, or are you going to get, like, I'll give you guys options to choose one. This is A, this is B.
Is it A?
Yeah, it two says A. I'll wait till everyone gives me the answer.
All three are like separate, right? Like A, B, C.
I feel like it's A.
A.
I too think it's A.
Okay. Kaveri and Adit?
C2H. Will A be correct?
A. Ha, good. All of you are right. A is the correct answer. So only this particular part from the Grignard reagent is what's going to form an alkane. So this is just
What will be the second product?
second product. It's going to be something like, let me clear the space here. You have the phenoxide ion. So this is phenoxide minus, so Mg and I. So Mg has like 2+ charge, right? So one side of the charge satisfied by phenoxide and the other satisfied by. This may disintegrate further, but like, yeah, we don't really care about that. Main thing is preparation of alkane. This is the alkane that we're going to get.
When will the class end?
Right now it's 5:30. I just wanted to stop at a sensible point. Okay. So if everyone has noted this down, I thought I could finish off preparation in this class, but no. So we have one more major method of preparation that also has like mechanism involved. So that's going to take some time. We'll resume next class.